much to the UKO main team for inviting me over today. So I am Konstantin. I'm a health data scientist, formerly part of the NHS England's data science team. And today I'll be giving a brief overview of our MM-HealthFair framework, which is very topical, following up on some of the ethical dilemmas of applying multimodal AI algorithms in the public health domain, specifically for risk classification. So in the current landscape of multimodal AI in healthcare, we're continuing to see algorithms achieving exceptional performance when predicting health risks and patient outcomes. But in fact, the majority of these algorithms often fail to actually translate into clinical workflows. So why that is? Well, one of the main bottlenecks of these algorithms is, in fact, being able to achieve this complex level of multimodal fusion while simultaneously being able to provide fair and equitable decisions. So in this case, multimodal fusion of complex medical data, especially when we're talking about the public health domain, does come at a cost of potentially exhibiting potentially harmful behavior towards patient groups that are underrepresented in the data. These could potentially favor patients with better access to health services, or those who come from a majority group in the population. So thus, we need careful safeguards in place to ensure that we are not essentially sacrificing fairness at the expense of increasing model performance. And this is where the main rationale behind this MM-HealthFair framework, which is designed to be an open source toolkit for investigating healthcare biases through measures of group fairness, especially when it comes to risk classification tasks. So for this purpose, we're using the Mimic4 database, which is an open collection of routine data from American hospitals, and it's suitable for deep learning multimodal pipelines for predicting patient outcomes. So in this case, the framework currently supports fusion across 3 modalities. So we have tabular, time series, and free text measurements, which can be collected from the patient's health records. And here we're representing an intermediate fusion approach looking into customizing individual deep neural components that we can tie into each data modality. So this gives us also the flexibility of choosing and investigating the different types of fusion. For example, we can opt for more simple feature concatenation or investigate more complex fusion with multimodal adaptation gates, leveraging some of the strengths from cross-attention layers. And our main contribution is basically looking into decision fairness on a holdout test set, and also looking into feature importances across different modalities, leveraging an aggregation of shapely values. So to test this framework, we did a quick case study on predicting extended hospital stay using this data, looking into measures of demographic parity and equalized odds. So first of all, we noticed that adding more modalities to the data notably boosts model performance. However, interestingly, this also tended to reduce predictive parity in some cases, in this case specifically burdening ethnic minorities in the data. So here we also proposed a feature importance component, which gives us a detailed overview on investigating why these biases happen on the individual level, looking into essentially relative scores to look at modality dependence, highlighting the degree to which a modality has influenced the patient's risk ranking. So once again, this work was conducted as part of a NHS England internship, so special thanks goes out to the NHS England transformation team, especially Sophie Martin, who worked on a previous version of this framework. So if you're interested in learning more, I'm happy to go over my poster in our session downstairs. And you can also scan the QR code to look into our code repository, and you can also find a detailed report listed there as well. So thank you very much for listening.
Thank you, Konstantin.